Hey everyone. In this video, we're going to be talking more about alkanes and their physical properties and where they come from and what they do. So first, let's take a look at where we get hydrocarbons from. So the main source is petroleum. So we pump crude oil out of the ground. So here's an image of a deep sea oil rig, right? We pump crude oil out of the ground, and it's a dirty mixture of hydrocarbons and other organic compounds that must be refined or separated into fractions that we can then use for other things. And so pretty much all hydrocarbons and industrial chemicals come from petroleum. So refining petroleum takes the crude oil and runs it through a refinery where they separate it into what are called fractions based on boiling point. So they heat up the crude oil, and some things boil off at lower temperatures, and then others boil off at higher temperatures, and they separate them based on boiling point. And so that brings us to our first physical property, boiling points of alkanes. So as the number of carbon atoms in an alkane increases, the boiling point increases. So let's take a look at butane versus pentane versus hexane here. The molecular formula for butane is C4H10. Pentane is C5H12, and hexane is C6H14. So you can see the number of carbons is increasing, and the boiling points are also increasing. And so this has to do with the surface area of the molecule. Molecules with a bigger surface area have stronger intermolecular forces. So stronger dispersion forces. That means they stick together better because they're bigger and they have a bigger surface area. So molecules that stick together better require more heat energy to make them boil away from each other. So higher number of carbons, higher boiling point. And so let's take a look at an oil refinery tower. So in the tower, they have separating layers, if you will. They pump the crude oil in preheated, and then different regions are maintained at different temperatures, and the fractions will come out at the temperature that corresponds to their boiling temperature. So you heat the mixture of crude oil, and everything that boils below 20 degrees Celsius comes off at the top. And so this is what we call natural gas. It's basically anything from 1 to 4 carbons. So methane, ethane, propane, butane, these all come out as natural gas. The next fraction is referred to as gasoline, which everybody's familiar with gasoline. And gasoline is anything that has a boiling temperature between 20 and 200 degrees Celsius. And so this includes carbons between 4 and 12. So any alkane from 4 to 12 carbons long comes out as gasoline. So gasoline is a mixture of alkanes. Kerosene is anything that boils between 175 and 275 degrees Celsius. And so that's hydrocarbons that are 9 to 16 carbons long. So your heavier carbons. And then the next fraction boils between 250 and 400 Celsius. And that's our diesel fuels and our jet fuels. So they're more dense carbons between 9 to 25 carbons long. So really thick, viscous fuels. And then lubricating oil is anything that boils above 350. And so this is like your motor oil, like super thick, dense. Those molecules tend to be alkanes with carbon numbers between 18 to 34. So really, really big alkanes are your lubricating oils. And then anything that doesn't boil off, your solid residue, is what we call asphalt. So we pave our roads basically with the residue left behind after we boil off all the good stuff. So let's take a look at each of these fractions in a little more detail. So alkanes are nonpolar. They contain only carbon-carbon and carbon-hydrogen bonds. There's no electronegative atoms, so they are nonpolar. They have relatively weak intermolecular forces, so they have low melting and boiling points, right? That's why we're able to separate them, is because they have reasonable boiling temperatures. The small ones are gases at room temperature. The larger alkanes are liquids at room temperature, and the really big ones are solids at room temperature, like asphalt. Alkanes are insoluble in water because they're nonpolar, and they're also less dense than water, meaning that they float on top of water. So whenever there's an oil spill in the ocean, so there's an image of an oil spill and a boat trying to clean it up. You can see that the oil floats on top of the water. It doesn't just sink back down to the bottom of the ocean. It stays on the surface. And it doesn't mix with water because it's nonpolar. So it doesn't just blend in with the ocean. It just sits there in a puddle on top of the ocean, which kind of makes it a nightmare to try and clean up. And it's highly flammable. So oil spills sometimes catch on fire. So then you got this burning puddle of fire on top of the ocean. It's just a disaster. So oil spills are really bad for the environment, and they're really difficult to deal with. So not that we're talking about oil spills in this class, but it's just an example of how alkanes are nonpolar. They insoluble in water, and they're less dense, meaning that they float on water. So the oil spill was the perfect example to illustrate those properties. So now let's go back and look at these fractions in a little more detail. So alkanes with 1 to 4 carbons are gases. These are what we call natural gas. The simplest is methane, 1 carbon. And this is what we use in our homes. So most of the gas that comes out of your stove is methane. Propane is 3 carbons long. It's a little more dense. And so if you pressurize it, you can compress it into a liquid. And this is what we use for our barbecues, right? Those 5-gallon propane tanks, right? Propane is just a 3-carbon alkane. Butane has 4 carbons, so it's a little more dense. And so this is a gas, but you can compress it into a liquid. And it takes less pressure to keep it in a liquid phase than propane, which is why we can have just a little plastic lighter keep it as a liquid in there. So you can see the liquid inside of the clear lighters. If this breaks open, that liquid immediately evaporates into gas because it's slightly pressurized in here. And that little bit of pressure is enough to keep it as a liquid. Whereas propane with 1 fewer carbons wants to be a gas even more so. And so you need a steel canister to keep it highly pressurized to keep it in the liquid phase. So just 3 examples of simple alkanes that are fractions of natural gas. So the next fraction is gasoline. So anything from 4 to 12 carbons. And so everybody's familiar with gasoline, right? This is what we use for fuel in our cars. So we ship this out in giant containers to gas stations, and then you pump it into your cars. The main component of gasoline is octane. So if you ever read the gasoline pump, it says there's an octane rating, right? Octane has 8 carbons. So this is one of the main components of gasoline. Although, once again, gasoline's a mixture. It's anything between 4 to 12 carbons. So octane having 8 carbons is just one of the components. So heavier than gasoline is kerosene and diesel fuel. So anything from 9 to 16 carbons is kerosene, 9 to 25 carbons is diesel. And we use those as more dense fuels. So jet fuel is kerosene, so usually around 10 carbons. And then motor oil is your larger ones. Motor oil is anything from like 18 to 34 carbons. So the more dense and bigger ones. And then the really large carbons, 18 or more, tend to be solids at room temperature. So these are your paraffins or your waxes. So here's a picture of just paraffin wax, little pellets, and then a candle made of paraffin wax. So this candle wax that you're familiar with is just an alkane mixture, anything more than 18 carbons. So they have so many carbons that they have a really high melting point. And so at room temperature, they're actually in the solid state. Now, all of these different fractions of alkanes, they all had a common reaction that we use them for. And that reaction is combustion. Right? The most useful thing that alkanes do is they burn. You can set them on fire, which not that exciting, but it's useful as a fuel source. And so this is the number one thing that alkanes are used for in our society. We set them on fire and we harness that energy either to cook our food, to heat our houses, or to make our cars drive down the road. We burn alkanes. And so in a combustion reaction, you're taking an alkane and you're reacting it with oxygen gas, and you're producing carbon dioxide, water, and energy. And so here's just Lewis structures showing you. So a CH4 molecule is going to combine with 2 molecules of O2. And it's going to produce 1 molecule of CO2 and 2 molecules of H2O. And so it's just a rearrangement of the atoms and the bonds, and it gives off a large amount of energy. And that energy being given off is the fire that you see. So let's do a study check. Propane is used as fuel in propane tanks. Write a balanced equation for the complete combustion of propane. So they give you the molecular formula here. So C3H8. In a combustion reaction, we're always combining it with oxygen, so O2. And what does that create? Well, we know we're going to be creating carbon dioxide and water vapor, plus a bunch of energy. Now I'm going to move this so I have more space to write. Now, we need to balance this chemical equation. So the first thing I'm going to start with is the C3H8, so that's the most complicated. And let's start with carbon. We see that there are 3 carbon atoms. And so that means we're going to come over here and write a coefficient 3. And that's going to give us 3 carbon atoms on this side. We had 8 hydrogens. So I need to put a 4 over here to give me my 8 hydrogens there. And then if I add up the total oxygens on the right side here, I've got 3 times 2 is 6, plus 4 is 10 total oxygens. So on the left side, I need to put a 5 there to give me my 10 oxygens on the left. And that is a properly balanced equation for the combustion of propane. So C3H8 plus 5 O2s makes 3 carbon dioxides and 4 waters. So to recap this video, we obtain hydrocarbons from petroleum oil We refine it in oil refineries where we separate it by boiling point. Larger hydrocarbons have higher boiling points. Smaller hydrocarbons have lower boiling points. And the thing we most commonly use all hydrocarbons for is combustion, where we set them on fire. And in a combustion reaction, an alkane reacts with oxygen to produce carbon dioxide, water, and energy. Thanks for watching, and I'll see you in the next video.